When we were covering image classification with convolution networks, we looked at some simple methods for visualizing which parts of the image were being more important in the classification. But now we're going to look at this problem of understanding what a deep model is doing in a broader context. So we're going to look at the motivation for trying to find interpretations or explanations and basically give some transparency to these black box models, and conversely the problems that we have if we simply accept the output of deep neural networks without trying to understand what is happening inside, without trying to look inside the box. And then we're going to look at some methods that are used to try to explain or interpret what these networks are doing. We're going to use explanation in a very focused and pragmatic sense of something that is useful to understand what the network is doing. And then we're going to look at some methods for local explanations, for trying to see the relevance of the inputs, and mapping concepts or associating concepts with what the network is doing. These will just be some examples, these methods. There are many other approaches, but this is to give you an idea of different ways of tackling this problem, but especially giving you a notion of how important it is to bring some transparency to this type of models, because this will also be related with the second part, the second lecture today, where we're going to look at problems of bias and fairness in machine learning and specifically in deep learning. So let's see why we want explainable AI in general, or in particular in our case, explaining the workings of a deep neural network. If you have a problem like organizing vacation photos, where you want to separate photos you have with your friends and selfies and so on, so photos with faces of people, and you want to separate them from photos of landscape and buildings and those that don't have people. So you can use a deep neural network to identify which photos contain people and separate them into different folders. Now, how exactly is the network doing this? Which features is it using? How is it processing the image? You don't particularly care, because for an application of this type, as long as it's mostly accurate and you just have to move manually a few photos, it's not a big concern exactly how the network is working. You are not developing the network, you're just using it for this very trivial purpose. So for these kinds of applications, we don't worry too much about explainability, about interpreting the models. But now suppose that a surgeon is using a deep neural network to process radiological images and give some recommendation about therapy for a patient. And the network recommends extracting the left kidney of the patient. Obviously, the surgeon cannot act on that recommendation without knowing why this is recommended, without having a justification for this that the surgeon can evaluate and understand what the problem is. So in these cases, when we have at the other extreme the outcome of a deep neural network recommending or doing something that will have impact on the lives of people, something that is important, in that case we really need to have some justification so that there can be trust and oversight and control over what the network is doing. So if you have an application of this type, it becomes useless to just use the network without the appropriate justification, because in that case the simple recommendation that the network is outputting will not be useful, will not be something that the surgeon can act upon, or any human who has to decide can act upon that recommendation without understanding how it's justified. So this gives you an idea of the motivation for explainable AI. There are many situations where we really need to understand what the network is doing in order to decide how to react to that. So one stage at which interpretation is important is in debugging or in trying to optimize or improve the system. So if you are developing these kinds of models for deep learning, it's very important that you use these kinds of visualization and interpretation methods in order to check if the results are appearing for the right reasons and not because something is going wrong. I'm going to show examples of this right away. But also another important aspect is how much we trust that the system is working correctly. If we don't understand how the system is working, then trust will probably be difficult when the system is recommending that we do something. Social acceptance also depends on this kind of understanding, so interpretation and explanation of the system. Systems like advertising recommendations and the control that these algorithms have over the feed that we see on social media and so on. Those things may be more easily accepted by the users if they understand how the system is working. Otherwise, there may be some reluctance in accepting how these kinds of systems. The guarantee that a decision was reached in a proper and fair way is also important, and we're going to talk a bit about fairness in the next lecture. But that problem is related to this problem of interpretability, because we need to understand what the system is doing in order to assess if the result is fair. And then there is all those problems of regulation, of accountability and auditing and so on. So if we are to authorize autonomous driving vehicles, we need to understand how the system is working. It's not enough to know that 99% of the time the vehicle doesn't crash. We need to understand how it's doing what it's doing sufficiently so that we know what are the conditions for it to work properly, how it will fail if something goes wrong, and so on. So everything that involves regulation, accountability, auditing will require some kind of interpretation of how these deep models work. And also sometimes it's simply to have a greater impact or usability of the network. So suppose that you have those purchase recommendations where you go to a shop and it's recommended that you buy this product or this other product. If those things come with an explanation, if they say buy this book because you also like this type and so on, those things may have greater impact than just giving the recommendation without justification. So our rational parts always look for reasons for doing things. So if we are given some advice and some recommendation for doing something, it's always better to justify that with some reasons. Okay, so let's look at a few examples of these. This is an example of classification of, this is the Open Images data set. No, sorry, the Pascal VOC data set. And the authors used this method for that I'm going to talk about later to check the relevance of the inputs, to examine some images. And what they found is that the classification of a horse was using the copyright tag of the image. So the relevant part of the image is this segment here. And if they removed that copyright tag, then the image would not be classified as a horse. And if they added this copyright tag to a car, then the car would be classified as a horse with the copyright tag, but not without the copyright tag. So by using this interpretation method, they noticed that in these cases, the model was not learning the right features for the classification. This was actually not a deep neural network, it was a different model, but the idea is the same. And we, using these interpretation methods, we can check if the results that we are getting are really robust and are really for the right reasons, and not because of some spurious correlations that we didn't notice in the data set, and the model is now taking advantage of those. So this is an example of the usefulness of interpretation when developing, evaluating, and improving these kinds of models. Trust is also something that depends a lot on interpretation and explanations, because When we use some tool like a microwave oven or a motorized tool or something like that, a saw, we are making the decisions ourselves. So even if you don't understand very well how the tool works, how an engine works, how the microwave oven works, and so on, we still can use it with some trust if we know that it's reliable because we are in control. The problem with artificial intelligence and deep learning is that we are using those systems to tell us what to do, to make decisions for us or recommendations or do something without us having to intervene and decide. And this requires a different level of trust. So transparency is necessary that people can trust these kinds of systems. And it's especially important when that trust requires some accountability and oversight. So you can trust that your microwave oven will not burn down your house because there are some people who understand how the microwave oven is working, and they guarantee through regulations and control of the processes of manufacture and so on that the microwave oven is safe to use. But if you have a deep model that no one understands exactly what is doing, then there will be no one that can be responsible for that kind of control, regulation, accountability, and so on, that would guarantee the model is working properly. So we really need to have transparency in this context, especially as we have the deep learning models interfering increasingly with the important aspects of people's lives. Another useful outcome of interpreting the models would be to really obtain some insight into what are the aspects that the model is using and how it is using them. For example, in recent years, these deep neural networks, AlphaFold and AlphaFold 2, have solved a very old problem, about 50 years old problem, of trying to figure out how proteins fold and how they have their structure. Proteins are very large molecules, they're important in living organisms, and they have very complex shapes. So as you can see, these previous algorithms that were used in bioinformatics until about 2016 in this contest to assess prediction methods, CASP, for assessing prediction methods for protein structure. They worked about with a score of 40%, 50%. This is an evaluation of the quality of the predictions and the success rate of the predictions. In 2018, AlphaFold gained a significant advantage over the rest, and in 2020, AlphaFold 2 really took over, so it's much better than all the others. Unfortunately, it's harder to understand how AlphaFold 2 is doing this, because if you are actually using algorithms that were written by humans, you know what are the different parts of the algorithm and what they're doing. If you have an algorithm that is basically a set of multiplications and sums with over a very large number of functions composed with each other, that was determined automatically by learning, then it's very hard to understand why it works so well. But it would be very useful if we are able to properly interpret these models, because then we would learn something useful about how proteins fold. Not just have a machine, a black box machine that predicts the structure of the proteins, but actually something that explains to us what makes proteins fold correctly. There are also legal requirements for transparency and explanations, interpretation of these models. The General Data Protection Regulation, not in legally binding parts, but at least in the recitals, includes the right to an explanation. So the idea is that if someone decides something about you, for example, you ask for credit to buy a house and the bank denies that, you have the right to ask why you were denied credit. So if the bank is using some deep neural network to evaluate your request and your financial situation and recommend denying you credit, there must be some way for them to interpret what the network is doing and explain to you why that decision is taken. Also, in the legally binding part in Article 22, the law stipulates that these decisions that affect people cannot be completely automated. There must be someone responsible for making the decision, even if they are the decision is based on recommendations by these machine learning algorithms. So this creates also this problem for the person that has to be responsible for the decision. If the decision is not fully automated, and someone must look at the outcome of, say, a deep neural network and then decide whether to accept that or not, this creates a need for some kind of justification for the outcome of the network, so that the person can decide if it applies in that particular case, if it's reliable, and so forth. So the legal framework that is currently being constructed will require some investment in interpretability, in explaining what the networks are doing. Okay, so one question. I've been talking here about different things: interpreting, explaining, transparency of the models, and the question here is, what exactly is an explanation? If we want to look at it in a broad sense, this is basically a narrative, a way that we fit together different events and entities so that we can understand causal relations, consequences, how this system works. But for the purpose of explainability in the context of this lecture, at least, and what we are focusing on for deep neural networks, we are going to take a more practical approach. We're going to think about an explanation as merely that which is useful to understand the part that we need for a particular purpose. So if you are trying to check if the classifier is using the appropriate parts of the image, then the explanation would be a kind of diagram that tells you what are the more important parts, so that you can check if this is working. If you want to see if the classifier is very sensitive to some kinds of things, like the stripe patterns on zebras or something like that, then a measure of this sensibility would be the explanation that you would require. So this is not really an explanation in the philosophical, scientific, or broader sense. Is a very narrow sense of something that is giving you an insight that is useful for that particular purpose. So one consequence of this is that we also always have to consider the target audience. If we are trying to build an explanation for a decision of the neural network that as a target audience, the surgeon that has to decide what to do with the patient and so on, then the best explanation in that context is unlikely to be the same as the best explanation for the patient to understand why he's going to be operated. So we need to think about the audience. There are people who need to decide. For example, in credit fraud detection, we have those that are monitoring and developing the models. They need to have interpretation methods that allow them to check if the models are learning correctly, if the data sets are properly balanced, and so on. And then there are the experts who decide if fraud occurred and what measures to take. And these would have different requirements for the explanation. So they would need different aspects explained in order to be able to make those decisions. So basically, the interpretation methods must be chosen taking into consideration both the target audience, the person that's going to benefit from the interpretation, and the purpose of this interpretation. So to this end, I'm going to give you a few examples of different interpretation methods. There are many more. We don't have time to cover everything, but to give you an idea of different approaches. So let's start with LIME. This is Local Interpretable Model Agnostic Explanations. It's a very large name, but the idea is that we are looking at explanations that do not depend on the model itself. So they are not trying to look at what the model is, and they are local to a particular example that we want to explain. The basic idea here is that some machine learning models are very easy to interpret. For example, linear models are easy to interpret because when you have a linear model, for example, here we have the problem with the three types of flowers that we saw previously. This is a classical example in machine learning. There are three species of flowers. They have different petal and sepal lengths and width, so we can use those features to separate the three categories of flowers represented here in blue, red, and green. If we use a linear model, then we are creating a decision function, a decision surface that is a function of linear combinations of the features. And the features will always be the same and combined in the same way for all the examples. So regardless of where we are, there is this vector that is perpendicular to the decision surface, and it will tell us to which side of the decision surface the example belongs. And this vector is a linear combination of the features that takes different features in different weights, so we can look at which features are more important for the classification. If we go to a nonlinear classifier, then the vector that is perpendicular to the decision surface, that is the combination of features that is being used for each example, will depend on the example. So in different places of these coordinates, we have different combinations of features being important for classifying each particular example. So this becomes a lot harder to understand because we don't know what the model is doing easily, because this is a lot more complicated. It depends on the different examples. What LIME does is to create a local linear approximation to what the nonlinear model is doing. So suppose that this complicated region here is the decision surface for a nonlinear model that separates these two classes, blue and red. This is very complicated, so the nonlinear model creates this separation that is very intricate like this. And it's hard to understand with the whole model, the nonlinear model, how each example is being classified. So what LIME does is, if we ask for an explanation of this particular point here, is to select points in the neighborhood, weight them according to the distance. So points that are far away are weighted with small weights. Points that are close together have larger weights. And then LIME will try to find a simple linear model that approximates the frontier at this neighborhood. So these are the classifications of the original model, the red and the blue. And LIME is trying to mimic the model we want to understand, but only at this local region and with a linear simple model. That way we can now try to understand in this neighborhood how this part of the decision surface is working. So here's an example of comparing two different models using LIME. We have the same example. This was a support vector machine with kernel transformation, but it's a nonlinear model that is hard to interpret. But LIME looks at this particular example, which is an email post, so a post to a news group. This is a bit old, this example, but news groups were the equivalent of social networks some years ago. And the model was trying to predict whether the post was defending Christianity or atheism. So this was a discussion group on religion, and the model was trying to distinguish between the two, atheism or Christianity. Both of these models got the prediction right, that this post was defending atheism, but one of the models had these components, these features that were being used for this particular example according to Lime. Things like God, Koresh, David Koresh was a cult leader, and things like that. And the other was using words like re in the subject in response to something, NNTP, the protocol used, and things like that, pooling and so on. So even though this model got the answer right, it's apparently looking at attributes of the message that are not really relevant for the kind of semantic interpretation we would need to properly classify as atheist or Christian. So this is one example of how, looking at how this particular example here was classified, we can have an idea of how well the model is working. So Lime does not provide a global explanation. It doesn't look at all the examples or all the landscape of that decision surface. It just looks at one particular example and does a local approximation so that we can interpret how that example is being classified. And it is model agnostic because it doesn't really look at how the model works. So basically we have this, the outcome of the model, this F, which is how each example is being classified, and we want to minimize this loss function between what the model to be explained has decided and this linear simple explanatory model that we have, G, given some neighborhood of points. So we're not looking at a whole data set, we're only looking around some specific point, and we want to make the predictions of this linear model, G, as close as possible to the predictions of the original model. So it will never be perfect because we're doing this linear simplification, but we want to minimize that. But not only that, not only the loss, also a measure of the complexity of our linear model. So if you have a linear model with thousands of different features and they all weigh more or less the same, then it's very hard to understand what the model is doing all the same. So you need to have a sufficiently simple model so it's interpretable. And this is a complexity measure. Basically, these different possible linear models that Lime is trying in order to minimize this expression use different combinations of features, and we have this measure of the features that the model is using so that we make it as simple as possible and as close as possible to what the model to be explained is outputting. So this is the idea. We're trying to fit the same results in a local region with a simple model, but we are not really looking at what the model we want to interpret is doing. We are just looking at the results and trying to fit that. So this is one criticism of Lime, because it's not really an interpretation of the model itself. It's just an explanation of those results if at the local level it was the classification was done with a linear model. So it's kind of strange, but I'm mentioning this because this is a very used interpretation method. So let's look at something that actually considers the deep neural network, the architecture, and the weights. This is layer-wise relevance propagation. And the idea here is that we have an example passing through our classifier. At the output, we have one neuron that is predicting one particular class. So suppose that we have 10 classes, we will have 10 neurons at the output, and we want to see the relevance of the inputs, for example, the pixels of an image, but this can be more general than that. We want to see how relevant each input is for that prediction of that particular class. And this is done by propagating relevance through the network from the end all the way to the inputs. And relevance is, for the output neuron, its activation. So we choose a class that we're going to check the relevance for, and we measure the activation of the neuron corresponding to that class. And now we propagate the relevance backwards by applying these formulas. So a neuron in a previous layer will have a relevance that is the sum for all the neurons in the next layer of the weight connecting this neuron J to each neuron K, multiplied by the activation of neuron J, so this is the expression here, and divided by all the products of weights and activations that this neuron is receiving. So basically the relevance this neuron gets is its own activation. The higher it is, the more relevant the neuron is, multiplied by the weight and the relevance of K, but this is normalized by everything, all the inputs this neuron RK is receiving. So this would be the fraction that this one is contributing to the inputs of RK. And now we can do this, compute this relevance going backwards along the network all the way to the beginning, to the inputs, and so we see how relevant each input is. This is an example. You can go to this site, Explainable AI. You have demonstrations of this. You can choose different examples. But in this case, we have a classifier. We notice that the strongest output is for the goldfish here. So we choose the neuron for the goldfish, and we're going to see the relevance of the pixels for the classification in this class. And now propagating backwards the relevance through all the layers, we see how relevant the pixels are. So basically the pixels here around the fish seem to be the most important, and also those here on around the eye and the gills and so on. And this makes sense for this kind of classification. If we obtained a map that was, for example, a tag on the image or something like that, then we could suspect that there was something wrong with our model. So a different approach, TCAV, this is testing with concept activation vectors. And this is not an attempt to attribute relevance to individual pixels, but rather look at this in a more abstract way to see how some concepts are influencing the classification. And the concepts here are defined by a set of examples. Suppose that we have a classifier that classifies some examples as zebras. So zebras are this class K here. And we want to see how important this striped pattern is for this classification. So first we need to determine explicitly what is this concept of stripes. And to do that, we create this data set that has stripe patterns that we chose to illustrate the concept that we mean, and also a random set of examples that can be from our training set that would not be examples of specifically the stripe pattern that we want. So we have two sets here, or a data set separated into two classes, and this is what specifies the concept that we want. Now we also have this set of labeled examples that we have for in our training set, and we have one example of this that we will want to interpret. For instance, we have this trained classifier. So the network is already trained, and we choose a layer in the classifier where we're going to see how this concept is present in that layer and how sensitive the particular example is to that concept in that layer. So the way we're going to do that is to use these examples that we selected, the ones that specify the concept we want and distinguish it from the absence of that concept. So this is stripe pattern, this is everything else. And we're going to pass these through the network and obtain the activations at the layer that we want. So using those activations for each of these examples, we are going to use a linear classifier to separate, using these activations as features, separate the examples that describe or that correspond to our concept, the striped patterns here, from everything else that is not a stripe pattern. And this will give us a linear decision surface that has a normal that is defined by this normal vector. So usually with linear classifiers, we have some hyperplane here that is the frontier between the two classes. And this hyperplane is defined by a normal vector, a vector that is perpendicular to the hyperplane. So this is the concept activation vector. It's this perpendicular vector here that is separating the concept we chose from everything else in the space of activations of the layer that we chose. So now what we can do is we take the example that we want to explain. The concept activation vector is already determined because this was determined for all these data that we chose to specify the concept. And what we do now is we measure the derivative of the output for the zebra class here. So we pass this zebra through the network. We have the activation of the output neuron for the zebra class. And now we compute the derivative of this output here as we change the activations on the layer that we are examining in the direction of the concept activation vector. So this is the limit as epsilon goes to 0 of the difference between the output of the neuron using the activations of the M layer here plus a fraction of this vector minus the original activation here. So how much is the activation changing as we change the activations of this layer in the direction of the concept that we determined here. And this will tell us how sensitive the classification of zebra is to the concept that we defined as stripes. Note that we are not really telling the network stripes, we are just giving a set of examples to specify the concept, but then we get this activation vector in which direction we're going to measure the perturbations to the output of the network. So basically, in this example, the network receives images. It then passes the images through all the network and classifies as zebras. But now, using these concept activations that we can create, stripes, horse, savanna, we can measure how sensitive this particular example at each layer is to these kinds of concepts. And this way we can see which are more important or less important for the classification. Going a bit further on this idea, I'm just going to talk briefly about very recent work. This is actually work done by a colleague of yours last year, Manuel Ribeiro. So he finished his master's here in computer science. And the basic idea of this interpretation method is to map these concepts. So the concepts are also defined by sets of examples. But instead of just looking at the sensitivity for classifying a particular example with a concept, we are going to map these concepts into an ontology. An ontology is a formal specification of different concepts and their logical relations, and gives us a set of rules that encodes our background knowledge into some area. For example, if we have concepts like the octagon shape, the red background, the stop letters and so on, we can define a stop sign in traffic signs as an octagon with a red background and stop written in white. So we can formalize in our ontology these relations between the different concepts and defining what a stop sign is. Or, for example, warning signs are triangles with a red border. So the category of warning signs, they all must have triangular shape and have a red border. This we can encode formally into an ontology, and there are algorithms that can reason over these ontologies and deduce some consequences of the facts that we present. So now we have a trained deep neural network, so something similar to what we saw here with TCAV, and we want to map from the activations of this network when we present some examples into particular concepts. So this part is similar to what we're doing in TCAV, which is to use sets of examples to specify the concepts and then map the activations there. But the mapping is done using auxiliary models such as small neural networks, and not just a linear model to obtain the concept activation vector. We are not using those vectors. We are just mapping from the activations of hidden layers in the network to specific concepts. And this can tell us when we present an example and the network classifies it, for instance, as a stop sign, this mapping can tell us whether the network is also creating representations that correspond to octagon and to red background examples in the hidden layers. So after mapping, we can use automated reasoning to generate explicit justifications for the network output. For example, suppose that we pass a traffic sign image in the network and we obtain at the output the classification that it is a stop sign. If we also see that the activations are signaling that the network is identifying the concepts of red and octagon in our ontology, the automated reasoning system can immediately explain to us that red and octagon are important features of the stop sign. So this could be a justification of why the network classified that image as a stop sign. So this would be an advantage. Mapping into the ontology would give us now access to all the automated reasoning tools that already exist in logic and in symbolic AI. This also allows us to have some insight into how the network works in general. So we don't need to just look at particular examples. We can see which kind of concepts are easy to map from the network to the ontology and which concepts are not. And these will be in general for all examples, because we are not looking at specific examples. We are examining the architecture of the network. And so the network trained for classifying traffic signs, it's very easy. We have a very high accuracy when we try to map things like red border, red background, octagon shape, and so on. So these things that are relevant for distinguishing traffic signs are easy to map these concepts into the ontology. But if we try to map concepts like blue or having a pole or other things that are not relevant for classifying the traffic signs, then accuracy drops significantly. So this is also gives us a way of looking at what the network is doing as a whole, and not for particular examples, and what kind of representations the network is finding when trained on that data set. And this can help us understand what the network is doing, how reliable it is, and so forth. Okay, so just a note of caution at the end. We talked a lot about the advantages of having transparency, interpretation, and all of these. But there is also a risk, because as you can see, given a complex model like a deep neural network, there are many different ways of trying to interpret what the model is doing. And this gives rise to risks whenever there are conflicts of interest. So suppose I request credit to the bank to buy a house, the bank denies credit, and I ask for an explanation. Now the bank can use many different methods of interpretation on the models that it used to deny me credit, and just pick whatever interpretation they think will be best for justifying their decision. So the outcome may be actually a way to disguise unfair decisions and harm some people. So the note of caution here is that transparency is important at the level of the deep neural networks, especially when they affect people, but it is not enough to be just transparent about the model itself. The whole process must be transparent and accountable. There must be accountability for it to work properly. Otherwise, it's very easy to adapt interpretations or to pick and choose which parts are more beneficial to whatever interests of the person that is giving the explanation. Okay, so to sum up, we saw the motivation for transparency. Basically, when we have very complex models like deep neural networks, it's very hard to understand how they're working, and they work like a black box. And if the outcome is important, if it's not something trivial like sorting vacation photographs, but if it's something that has impact on the lives of people, like helping medical doctors in scientific research, in deciding things about people, who to hire, who to give credit to, and so on, then this becomes very important that we really understand how these decisions are made. Not only for that, but for everything from the development of the model to legislation and regulation about how these methods are used. And then I gave you some examples of methods. Lime looks at the neighborhood of a particular example and does not care about what the model is doing exactly. It just tries to mimic what the model is doing. Uh, LRP is looking for the relevance of the inputs, each individual input, to some decision of the method. And then we have these more interesting approaches where we can actually define higher level concepts that are not just this pixel or this input, but something that we can describe with sets of examples, and look at what the network is doing in its inner representations of the data and how it's using those concepts. So in the case of TCAV, we are measuring the derivative along the vector that distinguishes between the concept and the absence of that particular attribute. Also we can try to map these concepts to ontologies, and then not only do reasoning over the concepts that are being activated, but also use the accuracy of this mapping to see what kind of representations the network is building inside. So we have some kind of explicit explanation of what things are important for this network. Okay, so we're going to take a short break, and we'll start at 5 minutes before 10. See you soon.